Assalamu alaikum. I hope all of you will be fine. In this lecture, we will discuss generation of three-phase voltages and currents. As we have already discussed in the previous lecture, a three-phase system is a system in which magnitudes and frequencies of AC voltages are same and the phase difference of 120 degree with respect to each other. As you can see here in this figure, there are three number of phases. This is the phase A, this is the phase B, and this is the phase C. The phase difference between phase A and phase B is 120 degree, and the phase difference between phase B and the phase C is 120 degree as well. Let the first voltage VA is equal to VA is equal to Vm sine omega t. Vm is basically the peak voltage or maximum voltage. So as you can see here in this figure, so this peak voltage is the Vm voltage or maximum voltage or peak voltage. So as we know, Vrms is basically equal to V maximum voltage divided by under root 2, maximum voltage or peak voltage. So Vmax will be equal to under root 2 times Vrms voltage. So we can replace Vmax with under root 2 times Vrms voltage in this equation. Therefore, phase A voltage will be equal to under root 2 times Vrms into sine omega t. So this is the voltage of phase A, as you can see here in this figure. So the equation of the voltage of phase A is VA is equal to under root 2 times Vrms voltage into sine omega t. Or we can write phase A voltage VA is equal to Vm sine omega t. And next voltage VB will be lagging VA by 120 degree. So the phase B voltage is, so the phase B voltage is VB is equal to under root 2 times RMS voltage sine omega t minus 120 degree. And similarly, the third phase voltage VC is VC is equal to under root 2 times Vrms sine omega t minus 120 degree. Sorry, minus 240 degree. Again, the phase difference between phase B and phase C is 120 degree, as you can see here in these two equations. So these three, so the equations of the three-phase voltages are VA is equal to under root 2 times Vrms into sine omega t. The equation of phase B of the voltage is VB is equal to under root 2 times Vrms sine omega t minus 120 degree. And the equation of the third phase voltage VC is basically is under root 2 times Vrms sine omega t minus 240 degree. So these three voltages will be present simultaneously. So the waveform of these three voltages are shown here. This is the waveform of the phase A voltage, this is the waveform of phase B voltage, and this is the waveform of phase C voltage. So as you can see here in this figure, VB lags VA by 90 degree. The voltage of phase B, so the voltage of phase B, VB lags the VA, voltage of the phase A, by 120 degree. So as you can see here in this figure, the voltage of phase B is basically lags the voltage of phase A by 120 degree. So similarly, the voltage of phase C leads the voltage of phase A by 120 degree. That is, voltage of phase C leads by voltage of phase A 120 degree. So as you can see here in this figure as well. So this is the waveform of the phase C voltage, and this is the waveform of the phase A voltage. Phase C voltage is basically leads the phase A voltage by 120 degree. So now the question is, why we are adding this statement? So now the question is, why we are adding this statement? The answer of this question is, because from the statement, we are going to draw phasor diagram of these three voltages. So the phasor diagram, so now we will draw the phasor diagram of these three voltages. So the phasor diagram is, let VA is the reference voltage. So let VA is basically the reference voltage. As we know, VA is basically equal to √2 times VRMS sine omega t. The phasor form of this voltage is VA is equal to V angle of 0 degree. So this is the phasor form of phase A voltage. So this is the phasor form. Let V is the reference voltage because the phase angle of this voltage is 0 degree. So the phase angle of this voltage is 0 degree. So that's why this is the reference voltage. So V is basically equal to, so this is the 0 degree. So this is the phasor of the VA. And in the phasor form, V is basically equal to V angle of 0 degree. So now we will discuss the phase B voltage. Phase B voltage is basically equal to √2 times VRMS sine omega t. The phasor form of this voltage is V angle of minus, sorry, this is the minus 120 degree, of minus 120 degree. So now as you can see here in this equation, the voltage VB is basically lags the voltage VA by 120 degree. So that's why the phasor of phase B voltage is, the phasor of phase B voltage is like this. So this is the VB, and this is the angle of 120 degree. So now we will discuss the phase C voltage. So as we know, phase C voltage is basically equal to VC is equal to √2 times VRMS sine omega t minus 240 degree. The phasor form of this voltage equation is VC is equal to V angle of minus 240 degree. Or we can write this phase as VC is equal to V angle of plus 120 degree. So we can write this phase as minus 240 degree or plus 120 degree. So now, as you can see here in this equation, the phase C voltage is basically leading the phase A voltage by 120 degrees. So that's why the phasor of phase C voltage is like this. So this is the phase C voltage phasor diagram, and this is the angle of 120 degree. So this is then this is also equal to 120 degree. So this is all about the equation of the three-phase voltage waveforms and the phasor diagram. So now we will discuss the equation of the three-phase currents. So as we know, this is the phasor of the phase A voltage, this is the phasor of phase B voltage, and this is the phasor of phase C voltage. In case of currents, phases of the generator connected to the three identical loads. So as you can see here, this is the load of phase, this is the load connected with the phase A voltage, this is the load connected with the phase B voltage, and this is the load connected with the phase C voltage. All the loads are identical, that is same. That is, the voltage across the phase A is same as the phase B and phase C. All the loads are same and equal. So as we know, according to Ohm's law, the current of the phase A will be equal to, so phase A current will be equal to, I will be equal to phase A voltage divided by the load across the phase A. The load is basically Z angle of theta. So this will be equal to V over Z angle of minus theta. And this will be equal to I, V over I, Z is basically equal to I, angle of minus theta. And the phase B current will be equal to IB will be equal to V angle of minus 120 degree divided by Z angle of theta. So this will be equal to V divided by Z angle of minus 120 degree minus theta. So this will be equal to I angle of minus 120 degree minus theta. And similarly, the current in the phase C will be equal to IC is equal to V angle of minus 240 degree divided by Z angle of theta. So this will be equal to V divided by Z angle of minus 120 degree minus, sorry, this is the minus 240 degree minus theta. So this will be equal to I angle of minus 240 degree minus theta. So these are the equations of the three-phase currents in three-phase circuit. So it is possible to connect the negative ends, as you can see here in this circuit, the negative ends of these three single phase generator and the loads together. So we can connect the negative end of the three-phase supply and the loads together so that they share a common return line called neutral. When we will connect the negative end of the power supplies and the loads with each other, so this common point is called neutral. We will discuss in the next lecture what is the neutral and how can we calculate the value of the neutral current. Neutral. So that's it from this lecture. If you like this video, kindly like and subscribe this channel. In the next lecture, we will discuss what is the neutral, how can we find the neutral current.